Leah here from LeahForSci.com, and in this video, I will show you how to analyze the graph for Proton NMR. There are 4 things you want to look at when analyzing the NMR graph. First, we'll look at how to analyze it, and then we'll apply it to a simple example. However, if you understand what I show you, you'll be able to take this information and apply it to more complex examples. The first thing you want to look at is the number of hydrogen types. Then you want to look at the splitting of the peak. You want to identify the number and types of neighbors. And lastly, you want to identify the cause of the shift. We'll start by looking at the idea of types of hydrogen. NMR, disregarding how the machine works, simply analyzes the types of hydrogen that you have on a molecule and the similarities and differences in how it relates to the rest of the molecule. So for example, if I have something like CH4, since the carbon is surrounded by 4 equivalent hydrogens, I only have 1 hydrogen type. Same thing if I have an ethane, which is C2H6. Since every hydrogen on this molecule is bound to a carbon that has a carbon next to it with 3 hydrogens, every hydrogen is essentially the same. If I look at a longer carbon chain, this is when the hydrogen types start to differ. For example, let's look at the molecule propane that has a total of 3 carbons and 8 hydrogens. Notice that every hydrogen on the terminal carbon is the same, and this is because there is an sp3 bond between the carbon and the central carbon, allowing the carbon to rotate and therefore not differentiating between any of the hydrogens. However, notice that this molecule has a plane of symmetry so that the carbon on the right is essentially the same as the carbon on the left, making the 3 terminal hydrogens on either side the same. This gives me 1 type of hydrogen. And then I have 2 hydrogens on the central carbon. However, these are different from the terminal hydrogen based on the fact that they are located on a secondary carbon, while the terminal hydrogens are located on a primary carbon. Let's look at one more example, a methyl cyclopentane, where the hydrogens will be represented by green lines, and I'll draw out the hydrogens on the substituent. The methyl substituent is different from any other carbon on the ring, and so the 3 hydrogens on the methyl are considered equivalent. The tertiary carbon on the ring has a unique hydrogen, making it 1 type. Next to that, I have 2 hydrogens on a secondary carbon. However, since this is symmetrical, the 2 lower hydrogens on the secondary carbon are also equivalent. If I move further to the left, it appears that the 2 hydrogens circled in blue, both top and bottom, should be the same as the ones I circled in yellow. However, the blue hydrogens have 2 hydrogen neighbors on each side, while the yellow hydrogens have 2 neighbors on one side but only 1 neighbor on the other side. This makes them different. And so in the molecule methyl cyclopentane, I have a total of 4 types of hydrogens as far as NMR is concerned. The next thing we want to look at is the splitting of the peaks that show up on the NMR graph. You will see many different variations, and we'll draw out a few examples. I will show you how to analyze them, disregarding the scientific aspect behind the NMR machine, and rather focusing on what this means to your interpretation of the graph. Let's assume that every hydrogen or hydrogen type has a single peak to show that it exists on the graph. If I have a hydrogen neighbor next to it, let's assume that the neighbor simply takes the peak and splits it once. That means if I have no neighbors, where neighbors will be represented by a lowercase n, I will have a single peak. If I have 1 neighbor, this peak is split into 2, and so I get what's called a doublet. If I take this doublet and add a second neighbor for a total of 2 neighbors, I simply add 1 peak, giving me what's called a triplet. If I add 1 more for 3 neighbors, I get what's called a quartet. The mathematical way of solving this is using the rule of n plus 1, where n stands for the number of neighbors plus 1 for the original peak. Therefore, I can simply look at the peak on my graph, count the number of tips that I see, subtract 1, so it'll be tips minus 1, and that will give me the number of types of hydrogen neighbors. Let's engineer this backwards. If I see 4 tips, 4 minus 1 is 3, that gives me 3 neighbors. 3 minus 1 is 2 neighbors. 2 minus 1 is 1 neighbor, and 1 minus 1 is 0 or no neighbors. There is one tricky aspect that can sometimes show up when analyzing peaks, and that's when you have 2 peaks showing up at approximately the same area on the graph. For example, let's say you see this on the graph. At first glance, it appears that you have 5 tips. That means 5 minus 1 is 4 neighbors. However, if you use what I call the hat trick, then you will recognize that this is not 1 peak, but actually 2. And the hat trick has to do with a mathematical formula that tells you the height of the individual aspects of the peak. But instead of applying a mathematical formula when you are crunched for time, draw a simple hat on the peak. Notice that when I draw a triangle over this peak, I wind up hitting every single tip. Same thing for a doublet. And the same thing applies for this complicated quintet. However, going back to my original peak, if I try to do the hat trick, notice that I have this peak right here that does not fit, and so I know that is incorrect. However, notice I can draw 2 separate hats, or 2 separate triangles, and this shows me that these are actually 2 peaks that are overlapping on the graph. You find the number of neighbors as you analyze the splitting. However, it's important to mark this on the pieces of your graph so that you can identify how the different pieces of the puzzle fit together. For example, say I have these 2 peaks on my graph, and I am told that the peak on the right represents 2 hydrogens, and the peak on the left represents 3 hydrogens. Assuming the rest of the molecules irrelevant, I can look at the peak on the right and determine that it has 3 neighbors, and the peak on the left only has 2 neighbors. Using this information together, I can say that if the peak on the left has 2 neighbors and the peak on the right is 2 hydrogens, then the 2 neighbors are the 2 hydrogens, and the same applies for the 3 hydrogens on the left that are the 3 neighbors to the group on the right. And that means that these 2 groups are likely connected in a way that gives me the rest of the molecule bound to a CH2 bound to a CH3. And last but not least, we'll look at the chemical shift, or the delta value, of the individual peaks on the graph. Your NMR graph will range from the number 0 to approximately 12, and the peaks will show up all along the graph. If you look at a table, you're going to see a very large and very broad set of number values telling you which functional groups cause the shift to move and how far to the right and left. However, instead of memorizing these values, I highly recommend that you practice recognizing them. For example, you might see on the table that the value for alcohol, or the hydrogen on the ROH, ranges somewhere from 1 to 5. This is a very broad number, and you can have any other type of peak show up within 1 to 5, so this will not help you identify that you have an alcohol. If, however, you recognize a certain set of basic values and practice identifying how they show up, you're more likely to get these values correct. The numbers and values that I do recommend memorizing are as follows. Between the values of 3 to 5, you're going to have your halogens. At approximately the number 7 is where you will have your aromatics, and ranging anywhere from 9 to 12, you'll have the terminal hydrogen on a carboxyl or aldehyde. You can analyze the other values that will show up, but here is my interpretation of the rest of this graph. Some will call it upfield, some will call it upstream and downstream, higher shifted or lower shifted. I break the table down into 2 very simple values. Towards the right, I call it boring, and towards the left, I call it exciting. By boring, I mean a carbon with hydrogens and nothing too exciting in terms of highly electronegative groups. If you have a straight chain carbon, the peaks will likely show up to the right, and that is because there are no highly electronegative atoms to deprotonate the hydrogens and cause them to shift left. However, look at your halogens. Your halogens are more exciting and therefore will shift your value towards the left. Aromatics are even more exciting because they have their own electric field, giving you values around 7. And finally, the hydrogen on a carboxylic acid or aldehyde are next to such strong groups, these will shift all the way to the left. There is one more peak you want to recognize. At 0, when you see a small line, especially with the letters TMS written next to it, don't worry about this. TMS is what is used to zeroize or create a basis for where the numbers will show up on the graph, and that is not part of your molecule, so don't worry about it. And now let's apply this concept to the example drawn here. Are you struggling with organic chemistry? Are you looking for information to guide you through the course and help you succeed? If so, download my ebook, 10 Secrets to Acing Organic Chemistry, using the link below, or visit leahforsci.com/orgosecrets. That's ORGO secrets. If you enjoyed this video, please give it a thumbs up and even share it with a friend or two. If you have any questions regarding this video, leave a comment below or contact me through my Facebook page at facebook.com/leahforsci. There will be many related videos posted over the course of the semester, so go ahead and click the subscribe button to ensure that you don't miss out.